Okay. Okay, hello everyone. We will be starting a series about the AP chemistry, and this series is going to record how did I suffer in this course. And today is the technically the second day of the school. Well, it's the morning, so it's going to be the third day, sorry. And we will just be going through the note to see what have we learned so far, and trying some homework question together. So let's begin. So this is the first day of the class, and yeah, we just go through the basic definition of the chemical reactions. And there's two important terminology. So exothermic reaction is heat is being released, and endothermic is heat is absorbed. So for example, H2O is formed, more energy is released. Okay, energy released is going to be exothermic, and the melting of ice, so it's going to absorb the heat in order to change the state, right? The temperature, the temperature of the water is going to rise. So this is endothermic. Spilling acid on skin. When you spill something, you're gonna feel the heat that's releasing on your hand. So this is exothermic. When holding test tube in your hand, and an endothermic reaction is going on the test tubes, the tube feel warm or cold. So basically it's grabbing our energy from our hand, so you're gonna feel like the energy is going to be removing from your hand. You're gonna feel cold, so it's cold. So this reaction, more energy is required than releasing, so there's heat here, but it disappears after the reaction. So this is endothermic. And which substance contains the stronger bond? So originally it has stronger bond, so it requires energy to break it. Okay, so energy bonding, this requires the input of energy to breaking the bond. Okay. And system. So system is basically where the chemical reaction is going on, and surrounding is anything that's around it but not directly participate in the chemical reaction, I think. And boundary is separating two things, like a container or walls or something. Well, there's three different type of system. Okay, system is open to atmosphere, and the closed system is separate from the atmosphere. Matter can leave, but energy cannot leave, or enter, but energy can. They both can leave. So isolate system is the absolute, nothing can escape, but it's quite rare to have such a system exist. And thermal energy, the total amount of the internal energy of a substance related blah 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 blah. We don't need to know that. The only thing we need to know is it is measuring how hot or how much energy it has internally. Okay, temperature is the higher the temperature, the higher the average kinetic energy of the particle. So this is directly proportional. This is an important point here. And intermolecular potential energy. So, I think. Wait, hold on. Okay, I don't think we need to know this. And let's just skip the part. Okay, so what's going to be important is we are not going to calculate directly the thermal energy. We're just going to finding the net change before and after the chemical reaction, and the transfer of the okay, doesn't matter. So this is the formula. Q equals to MC delta T. This is going to be the equation to calculate the heat that's being transferred. Okay. And QMLF Oh, okay. Well, we are just calculating the relative, so like the actual amount it doesn't really matter. And yeah, we can just take the final temperature, I think. Okay, now let's don't care about that. Now, okay, the latent heat amount required. Oh yes, the one that required the state change. Because when you are changing from like a solid to a liquid to a gas, you're gonna have an energy to change the state. Like it does not go like a straight line and happen immediately. It requires some energy between each state change. Okay. And okay, there are two questions here. Which has the average kinetic energy? So we know that the kinetic energy is directly proportional to the temperature. So we pick the higher temperature coffee. And which one has the greatest thermal energy? Since it has like a lot of amount, so it's going to be bathtub. Okay. Okay. Oh, I'm gonna do this. Wait, hold on. Okay, this is just a note. I'm not going through that. Okay. And enthalpy. Okay, I don't know how to pronounce it, but that's not the point. Delta H is the change in enthalpy. It's called the heat of reaction. Represent using delta H. Okay, we're gonna the product minus the reactant equal to the constant. Okay, so this is a state function, and method A, this shows that delta H value, blah, 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 blah. Okay, there are three different methods, okay? And the first one is to write the delta H at the side, and we can tell this is exothermic or endothermic. And the second one is we just put the amount of delta H inside the chemical reaction. The third one is drawing a diagram. This is going to be the name of the reactant, and this is you're gonna put the reactant and the product under the line. Okay. And yeah, so if you can see delta H, if this is positive, you're gonna require more heat on the left side of the equation. Therefore, this is going to be endothermic. If you subtract energy, that means that some of the energy that's originally inside the reactant is going to be transformed into the heat into the surrounding. Okay, that's going to be exothermic. And yeah, more heat is required and the heat is released. Endo-exo. And yeah, like originally it has so much energy, but there's more energy in the end. It must take some energy, so this is endothermic. And it has a lot of energy at the beginning and less energy at the end, so it's going to be like losing some energy to the surroundings, so this is exothermic. Yeah, this is just some practice, and those are the different type of enthalpy, okay? And yeah, the standard temperature, standard pressure, yeah, just know that, okay? With most of the questions, just assume it's under those conditions, the standard state and standard enthalpy. Okay, let's see if there's anything else I need to talk about. Yeah, we just need to know what is like the standard state in those, like water. It must be liquid under those temperature and pressure. And yeah, so this is just a calculation. Okay. If we want to show one more, basically just balancing the equation. There's nothing much to show about here. Okay. And here, okay, okay, this is a little bit important. So the combustion and the formation are the only two chemical reaction we need to remember, because they are going to just say in like the methane, the combustion of methane, and calculate blah 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 blah. You're gonna expect it to know this equation. We know the product is always going to be carbon, and water is a reaction is going to like carbohydrate. No. Hydrocarbon and the oxygen. Okay, formation has three different properties. One mole is formed, and it's formed from its element and is in the standard state. Okay, most of the so the first one, for example, you need to check those numbers are exactly 1. And the second one is formed from element directly. So it means that the reactant must be different element. It cannot be like this. This is a compound. It must be a singular element. Each one is shown in the standard state. So for example, this one, carbon should be a solid in its standard state. It should be a solid. You know, the black solid that has high conductivity. That's why this one doesn't count. Okay, and yeah, there's nothing much to talk about so far. It's just like 2 days of school, and we can take a look at some of the problems that we have been doing. Let me check it for you. Okay, this is some of our homework, so it's kind of messy, my note. For example, the one formula that we will be using the most is going to be the MC delta T to calculate the amount of heat that is being transferred. So the delta T is going to be the difference of the temperature. For example, this one, minus 5 subtract minus 15, so it's going to be 10. It rises the temperature by 10. Okay. And you times the heat capacity of the ice, which is 2.5 joules per gram. Okay, and the mass is going to be 40 grams. So you're gonna multiply that. You go get so much joules. And more mass of water is just very similar. MC delta T. You just rearrange the equation. And the question 6 is very interesting, so it requires you to calculate the heat capacity. You can actually take the average and calculate the heat capacity of the substance. Like this, we have like 100 grams of like unknown, and C1, let's say that's the heat capacity of that unknown substance, and the 200 grams of like water. And then we take the average of the weight, okay? Just like when you are finding the centroid of a substance, okay? And that's going to be the heat capacity of your mixture. And you just sub it into the equation and solve for that. And okay, let's take a look at an example of let's take a look at example of what? Let's take a look at question 11 to make sure we cover all of the question types. So how you're gonna do it, you're gonna first calculate that how much of weight, how much amount of heat has been transferred. For example, this question, okay, let's take a look. Okay, so what amount of water can be heated? So we can first calculate how much heat is being transferred using the delta H. So how we gonna do it is that this one is a little like glitched. So -1 here, it should be like /mole and without -1 per mole, but it's understandable. So we get the mass, and we can calculate. We get the mass of butane, and we can calculate the molar. we can get the molar mass, and which is the formula for carbon, and each carbon is 12 grams, and the hydrogen, each hydrogen is 1. So the total molar mass, okay, the molar, like, okay, I don't know like the term, so how much gram is per mole, and we divided that to the mass, that's how much mole it has, okay, and how much mole, and then we multiply the delta H, that's how much energy per mole, and we're gonna get the total of energy that's being transferred. And when we divided, okay, that's how much total heat, right? When we divided that by the mass and also the, oh wait, hold on, we need to find the mass, never mind. So we need to divide the heat capacity and also the change of the temperature, and that's going to be the mass, because we arranged the MC delta T, right? This is delta T, this is like C, and this is M, this is Q, okay? Let's take a look at another one, okay? Okay, let's see another interesting one. So this one. So this one we need to find the okay, what do we need to find? Okay, this time we need to find like the substance that's being burned, not the like the change of the mass of water or blah 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 blah. So what we're gonna do is still calculate the amount of heat. We use the MC delta T. So this is the change of the temperature. We copy that. That's going to be 18, I guess. Wait, hold on. Huh? Yeah, I think I may have made like a calculation error, I think. Wait, hold on. Oh, that's 14. Sorry. Hold on. Yeah, that's the change of the temperature. And that's going to the heat capacity, and that's going to be your mass, okay? And just remember that the heat capacity is measured in like a joules per gram, like blah blah blah, per grams and per degree. So that's going to be gram. That's very important. And once we have the total amount of heat transferred, and we divided that by the okay, the changing of the mass, and we have the mass of the change of the mass of the candle, and that's the amount that's being burned. And we also need to, okay, let's see. Okay, that's how much amount is being burned. And that's how much energy being released, like joules per gram. And we, okay, never mind, this one is cal per gram. Okay, and yeah, we just need to convert that from joules to cal. So what you're gonna see more in the question is that you're gonna find like the delta H, in which is like it's like joules per mole. Like once you get this, right, you're gonna get the amount of energy released per gram. You're gonna multiply by how much grams is per mole, and just like what we did, earlier. I forgot which question we did, but just like this one, like we're gonna find the molar mass converter, okay? And we're just going to multiply that, and we're gonna get how much energy is per mole, okay? That's more you're gonna see in the question. And that concludes the video for today. Thank you for watching, okay?